Thank you so much. I want to thank the organizer for inviting me for this plenary speech. It's really a pleasure to be here. I don't be long. I hope to be short, and I will try my best to finish on time. So today I would like to speak about creating a new generation of functional multi-material fatigue-resistant solid-state joints. The outlines of my presentation will be a brief introduction about myself and about my previous research, challenging design of weld structures, solid-state joint in a kind of historic perspective, an introduction of the solid-state process that I want to introduce you today, the status of this solid-state welding technique, how this welding technique allows to obtain very high strength resistant fatigue components. And I want to discuss in details the bonding interface and what is happening down in scale with some concluding remarks. Dealing with the introduction, I want to say that I'm in NTNU from 2016. We have created a large group of people that I want to thank in this lecture that are reported here. We have around 20 PhD students in the group, 50 master students every year, and 10 visiting researchers every year. And this is the people that are present here from NTNU from the group and from the picture taken yesterday night. Today I will go a bit outside my comfort area. So usually I have worked a lot for more than 15 years developing local approaches for predicting fatigue strength and for making assessment of fatigue failures. And especially with Professor Paolo Lazzarin, that was my advisor in Padua, we developed a local criterion based on the strain energy density, of which I will not talk today, but I want to briefly introduce. That was my initial part of my research activity. More recently, I have focused on additive manufacturing from different aspects, and especially to architect cellular materials, where we have published several papers, also in some good journals. The last one is a recent paper published together with Professor Robert Ricci in Nature Communications, where we have studied nature-inspired additive manufacturing materials. And we study, in particular, three kinds of configuration, improving the fracture strength and fracture toughness contemporarily. And we study, of course, the fracture propagation in these three different configurations. Dealing with the architect materials, which is one of the research topics that I'm currently working on, we have studied the effect of from nanoscale to macro scale. And what it is interesting and is very important in this lecture is that the distinction between material and structures becomes less obvious if you look down at nanoscale. And so we were able to predict with some advanced numerical models of the structures for the first time the failure at nanoscale. But now we go more in detail close to the topic of these lectures, and I would like to introduce a bit the challenges that we have in the design of welded structures, and especially in the design of welded structures against fatigue. So why we are still focusing on fatigue after so many years? Because fatigue is the cause of most of the failures in engineering components, and actually is affecting 3 to 4% of the gross domestic product of European countries. Not only mechanical, but also civil structures has a lot of impact dealing with fatigue failures. And fatigue is local and not multi-scale, which has a very great scientific interest. In particular, we have three challenges that are still open. Strength and toughness paradox is not resolutive for fatigue design. Fatigue is still the root cause of most of the failures, and this is the engineering challenge. Fatigue is still the less understood damage mechanism, as well explained in a recent paper published in 2020 by Professor Robert Ricci. And the state-of-the-art approach has still limitation. Of course, every one of us has proposed something, but still we miss a kind of unified criterion. And so if you consider a large structure like this, what happens is that a structure that can be many meters in length and very wide fail for a very small crack close to a weldment that can make the structure collapse with many people dying. And was an example from North Sea from 1980. But this is not the example that was the last. We had more recent failures from 2014, where the welded structure fails under wind loading and multi-axial loading. So, and another design challenge is that sometimes we have to deal, I was involved in this project, in the design of very large structures that are called megastructures, where we have, for example, 1.3 million notches for 16 gates and 1.4 million of weldment multiplied 16 gates. How to deal with this problem against fatigue? This is not easy. But we have some tools that have been developed nowadays that can help us to solve this issue. This is another example, that is the Extreme Large Telescope in Chile. And another problem with or another design challenges with fatigue is that, of course, we have local approaches. We have some criteria that are able to consider that are mesh independent. We are able to consider in some way the scale effect, but still we have open challenges in the design of thin weldments, still a problem with multi-axial loadings, three-dimensional effects, and of course we have problems with computational efficiency for megastructures. And about manufacturing challenges, I mentioned only the one from friction stir welding. We know that, of course, we have some advantages. Not filler material is used, no problem related to material melting, but we have still open challenges related to different microstructural zones, defects, weld misalignment, microstructural changes, and the flexibility of the process that is quite low. Of course, we have, as I said before, some new tools that are coming, and data-driven methods can help a lot in this direction, but we have a lot of open questions how to apply this for the fatigue design of welded structures or fatigue design in general. We have, for example, some new tools like supervised learning that are able to consider geometrical effect, damage mechanism, and constitutive equation, but we are just at the beginning of this long path. And so, if you look to the literature, there is a nice paper, review paper, just published in Fatigue and Fracture, where there is a review of the application of deep learning for fatigue design. And it is worth of mentioning that 251 papers have been published recently in 2020 and 2021. But these papers were mainly focused on deep learning to design in a structure to proper objective without any attempt to inversely design fatigue resistant structure. And so instead, I think that this is the key to discover and design a new generation of high-performing materials in the direction where we have to go in the future. What I mean for direct design or forward design, it means that from a material architecture, we want to predict the one or more properties of the structure. This is the direct or forward design. The inverse design is given a target properties, we want to predict a novel high-perform structure or material based on these characteristics. And we are working on this topic with some of the people in my group. But the future will be for sure to consider different aspects of machine learning that is based on physics-informed machine learning, Bayesian optimization, sparse regression, graph neural network, understanding of interplay of material architectures. But dealing with joining techniques, we have room for a lot of improvement. And I want to say that solid-state techniques is quite recent, and the first one to propose a kind of cold welding was Desagouliers in 1724. And the idea of cold welding is to remove the oxy layer and apply compression and deformation to obtain metallic bonding. The history of this is concentrate mainly when friction stir welding was starting here, so it's quite recent. And I-bond, the process that I will describe now to you, was really recent. So an introduction to I-bond process. I-bond process is a solid-state technique that has been developed in NTNU from Professor Oinstein-Gronk with the collaboration of our persons, and I was working in the group. And is based on the idea that a filler material for civil plastic deformation is pressed against the two parts that you want to weld. And The advantage of the I-bond technique is that you have a low temperature, less than 400 degrees. Of course, originally it was taught for aluminum alloys, but after that I will show you later that is a multi-material welding technique. Has high geometrical flexibility and the capability to be scalable to different dimensions with a continuous extrusion at high pressure and a combination of oxide dispersion and severe plastic deformation. As I have said to you, there are a lot of possibilities with I-bond, and actually you can use I-bond for simple geometries, but also for more complex geometry, up to a kind of multi-material combination of different materials. In this figure, copper, aluminum, titanium, which were bonding together with this technique. We study the status of I-bond, and in particular I will be focusing on aluminum welding and aluminum steel welding. Dealing with the status of I-bond for aluminum welding and comparing this technique with gas metal arc welding and friction stir welding, we have seen that actually under static loading we have almost the same ultimate strength of the bonding of the friction stir welding. And the welding efficiency is almost similar. So these are some results and some picture of the weldments for 2 millimeter thickness with the efficiency of the weldments with respect to the base material. The advantage is that for I-bond we have a clear advantage in terms of speed and flexibility. And in particular, if you compare the speed of the friction stir welding with the speed for I-bond, we have a very nice advantage for I-bond, which has a speed of 8 millimeters per second. Instead, the friction stir welding is only 1.3. The heat affected zone, or the zone that is affected by the welding, is also very limited, and this is a strong advantage for residual stress that after that reflects also in very good fatigue properties, as I will show you later. Another important aspect is that the I-bond, at least under static condition, was found to be very, very strong bonding. And in fact, actually, we have a failure that is not happening at the bonding interface, but is mainly failing in the aluminum part. So the bonding resists under the static loading condition. And why so strong bonding has been found, I will explain later going down in scale. About the aluminum steel welding, we have still better advantages. Actually here, in terms of strength, we have plus 29% more than friction stir welding, and the speed is multiplied times 9. So the speed of I-bond is much higher than the speed of friction stir welding. Now we go to the focus of this talk, and this is the fatigue strength of these joints. So we made a full classification or a full analysis of these bonded joints. I will not report everything here, but going to the fatigue properties, we study fatigue behavior of aluminum with thickness 2 millimeters. And what it was quite interesting for us is that in this graph you can see that the base material and the I-bond has almost the same fatigue life. So this means that the fact that we have a bonding line is not really affecting or reducing the fatigue life in comparison with the base material, which is quite impressive, and we will understand later why. If you compare from the literature I-bond with different other techniques, it is evident that, which is the green line here and the red line here, it is evident that we have a strong advantage of I-bond. The comparison is made taking into account of the range of thickness that we have used for the test. So also for friction stir welding and gas metal arc welding, we are considering welding of 2-3 millimeters. Now we go to the most complex part, which is the I-bond of aluminum steel. You know that aluminum and steel does not like to be boyfriend or girlfriend together. So it's quite difficult to obtain a very good bonding between these two materials. And so what we have tried to do was to use I-bond for this purpose, and to control the intermetallic compound that was obtained with the iBond process during the process. So the preliminary results for aluminum steel weldments is referring to a thickness of 4 millimeters. And the intermetallic layer plus the mechanical interlocking of that I will explain later is giving the iBond strength of these joints. Dealing with the fatigue results, the failure was happening at the weld toe for the as well the components, and where we have when we have removed the over metal, of course the weldments, still the failure was happening in the interface. But again, if you look the base material with respect to the iBond machine, we have almost the same fatigue behavior. This means that actually to have the bonding or not to have the bonding is not really affecting the component, at least for this thickness. There are not relevant aluminum steel data available in the literature, so we have compared our aluminum steel data with the data from aluminum welds present in the literature. And what it is evident is that iBond is here. So for the B material, we are over what is happening for aluminum steel, which is quite good and much higher than Eurocode 9. This was not only a kind of study at university, but we also applied this to a real case that was the Johan Sverdrup living quarter for Equinor. And these welding were applied to this offshore platform. All the qualification made independently by Equinor, which is the ex-Statoil, have passed the requirements for the application of these weldments in that kind of real critical structures. What is happening at the bonding interface is another interesting question that I would like to discuss with you. Which is the size of the intermetallic and which is the shape of this intermetallic that allow a so high strength in this material. And so if you look down in scale, the first consideration is that the process is able to extrude the grains in the bonded lines. And so the severe plastic deformation is strongly occurring during the process. Another interesting observation is that if you study the SEM surface of this of the aluminum steel weldments, it is evident that we have a clear sign of mechanical interlocking at a smaller scale. And this is one of the most important effects for the fatigue purpose that I would like to discuss with you later. If you go down to the TM studies of aluminum steel interface, we have still clear sign of mechanical interlockings. We have investigated different points of the weldments, and we have looked at the TM, what was happening, and actually in any points where the bonding was fine, we have found the mechanical interlocking in the structures. And if you consider the TM studies of the interface and you measure the intermetallics, what it is important to note is that for traditional friction stir welding, we have an intermetallic that is usually 1 micrometer. And this is critical because sometimes the cracks propagate from the intermetallics and cause the failure of the components or of the bonded connection from there. But if you look down in scale, the iBond, what is happening is that sometimes the interface is very sharp and it goes to 5 nanometers. And in other case, it reaches as maximum 25 nanometers, which is quite impressive. And making the micro tests taken from these weldments, it is also evident that under static condition, the weldment is not failing and still the aluminum part is failing. So the bond is very, very strong. This has been applied also to multi-material weldings, aluminum, steel, titanium, copper, weld together in one single pass. And what was happening, I will only focus to titanium aluminum interface, is that again you can find clear sign of mechanical interlocking, which is a geometrical effect that is able to improve the capacity of loading of these weldments. And in fact, if you study the static properties at the welded lines, we find a high repetitive results with high strength of the bonding on the bonded condition. But interlocking materials are very interesting, and some recent papers have been published in this topic. These are mainly based on geometrical effects that I want to stress again are very important for fatigue design. And in nature also we found example of a lot of interlocking mechanisms. How nature is able to obtain high strength, high tough materials is due to some of these mechanisms that are able to control not only the gradient of the structures, but also the interlocking mechanism at the interface of these structures. And the other example in nature have shown that actually we have different interface where the interlocking mechanisms, which are geometrical mechanisms, are very important for fracture strength and fracture toughness improvements. This is a recent study from Professor Chao in Chao Gao in our group that study the interlocking mechanism in this kind of seed code, showing that it's possible to tune the interface with different wavelength and to obtain different value of ultimate strength and also fracture toughness of the material. But this is another example that we have studied recently with another student working, for example, on this kind of structure that is the shell of this animal. But strong and tough material can allow us to obtain high strength and high toughness material. What about fatigue? Although strength and toughness paradox is not resolutive for fatigue design, of course, to have a kind of interlock at the macro scale, interlock surface at the macro scale allows us to improve substantially the fatigue life. So taking this in mind, we have tried, starting from a bio-inspired case, or from this bio-inspired case, to apply machine learning technique or data-driven methods to enlarge the design space and to be able to obtain a kind of set of new design structures that were able to improve the strength and the toughness in parallel. And the preliminary results, not already published, have shown a very good agreement and a very good application of machine learning with the capacity of completely enlarging the existing design space with data-driven methods. Of course, dealing with fatigue, up to now we had empirical solution, theoretical solution, numerical solution, to which we of course strongly contribute, and my contribution was the strain energy density approach. But up to now we have in front of us a new era, which is the data-driven solution, where we can place fatigue in a new data-rich world. And in fact, some inspiring preliminary results, I will not comment on it, but can take into account with data-driven geometrical effects, material models or constitutive laws, and loading conditions all together. And these results are under publication in some different journals. So this is a kind of future step of my research. I would like to study better what is happening down in scale in the nature-inspired materials, and after that transfer to geometrical features to real structures. As well explained in this sentence, look deep in nature and then you will understand everything better. But what is happening if you go down in scale with die bond has been already made in a project that was financed by the Research Council of Norway, and the project name is insane because no one of us believed that that was possible. So we tried. So we used the idea was to use I bond for reproduce welding in situ, and the idea was to use the hybrid an hybrid needle of the fib, so truncate the real needle of the fib and put the filler material here to weld on the base material. And so the idea was actually to have this filler material. This was the base material. We performed some numerical analysis to understand the the capacity of this and how to design better the inclination of the hole. And after that, finally, we were able to obtain the first in situ welding component, welded component. It's nice because the needle is breaking here at the interface, and that part remains welded in the base material. This is another experiment, real-time experiment, where we would like to see the effect of this plastic deformation on the edge of the hole. So we make a kind of half of the hole and the visible part, and we apply the same load to see the severe plastic deformation occurring at the edge here. Of course, in this case, the bonding was not occurred because the hoop stress was completely missing. Concluding remarks, I think I was quite efficient. Advanced welding techniques are extremely powerful, and of course we have seen that we have still room of improvement. Geometry plays a key role that sometimes is underestimated from material science for fatigue design. And looking down in scales is of course fundamental and can help us a lot to understand a lot of these mechanisms. The future is to place fatigue in a new data-rich work, and bio-inspired fatigue design can have a really huge impact in the future. We can design structure at different scale, down to the atomic scale, but it's quite nice to see that at a certain level, geometry and material tends to coincide, and this helps a lot, especially under fatigue loading, where we stay always below or close to inside the elastic regime. So I want to thank also the support of the Italian group of Fracture, the picture that we take last night. And I want also to give you an advice. Don't go too much in the swimming pool, because this is the effect after 3 hours of heat treatment. I don't want to joke much because Paolo was my professor of metallurgy at University of Padua, so I cannot make so much. And I want to thank the sponsor for this opportunity and for the help that they give during the project. So thank you so much.